Okay, thank you. I'd like to thank the organizers for letting me speak here. And I'll be talking about this work that we started 3 years ago and we finished last night, but after the deadline, so it will appear tomorrow. So the original work, the first paper was in collaboration with Josif Ben and Nick Halmaji, and then our student Gregory Yekol and Stefano Masai joined the collaboration, and this last paper is with Josif, Stefano Masai, and the postdoc Stanislav Cooperstein. So the motivation for this work is twofold. So one is the work of interrogators Cyber and Xi, in which they found that rather simple gauge theories like SUN colors SQCD with NF flavors have a metastable vacuum. So there is a vacuum, there is a local minimum, and then farther away, separated by a barrier, there is a supersymmetric vacuum. And so there were immediately, people found many realizations in string theory of metastable vacua, but they were all in the Xi string going to zero limit. So the question is, what happens? Do these metastable vacua survive in the back-reactive solution, so when Xi string is not zero? So this is one of the motivations, and the other motivation is what Gary was talking about, which is the KKLT construction. So this metastable vacua coming from anti-branes, so I will tell you this construction in lots of detail, the construction of Kaczor-Pearson Perlinde. It was supposed to give rise to metastable vacua, and these were used, so these anti-branes were used to raise the cosmological constant, uplift the anti-de Sitter to de Sitter. So how this metastable vacua from anti-branes works. So we will concentrate on this setup, which is placing anti-branes on Klebanov-Strassler. So on the supersymmetric configuration of Klebanov-Strassler, which is in terms of the internal, the 6-dimensional geometry, is a cone over T11, which is like ns2 times ns3. The S3 has a finite size at r equals to 0, while the S2 shrinks to 0. And then we place anti-D3 branes here, and they are attracted to the bottom. So this configuration has positive, it has fluxes in such a way that it has positive D3 brane charge, and we're adding negative D3 brane charge. It goes all the way to the bottom. And because there is a topological Ramon-Ramon flux on this S3 with units m, what happens is that this F3 pulls this F3 pulls the D3 bars into an NS5, so they polarize into an NS5, and then there is this happens perturbatively, and then there is a non-perturbative mechanism that unwinds. So they wrap NS2 inside the S3, and there is a non-perturbative mechanism for unwinding and going back to the south pole, going to the south, not back, but going to the south pole and converting to regular supersymmetric D3 branes. So this would be the metastable state. This is the local minimum that I talked about, and this is the global minimum, the supersymmetric state. So what happens if you look at the charge, the D3 brane charge at some point, some radial point in the UV, what happens is if there is NS charge in the opposite cycle, so wrapping the S2 times the radial variable, then the D3 charge, this H3 and wedge F3, they contribute to D3 charge, so this D3 charge is K times M, and then minus n bar if we have n bar D3 branes at the bottom, so in this state. While in the supersymmetric state, what happens is 1 unit of NSNS charge gets annihilated, so the anti-branes annihilate, there's a brane flux annihilate versus 1 unit of this, and then they convert into m minus n bar D3 branes. And we will use this color coding of red for the anti-D3 and blue for the D3 state. So Kaczor-Pearson Perlinde indeed computed the potential for this, the potential for this, the D3 bar branes or the NS5 brane, and they found the local minimum. So this local minimum is at some size 0, which is where the NS5 brane wants to sit, and indeed it looks like the interrogator Cyber and Xi, so the metastable state and then the supersymmetric state. But now this is computed in the probe approximation. So here we're not taking into account, or they were not taking into account the back reaction of the anti-D3 brane. So the question is, does the metastable states exist at G string non-equal to 0? So when we take into account the back reaction of the branes. So this is what we want to answer. And so it's been 3 years of work, and now I can say that we're pinning down the answer. And if you can read in between the lines or the words, you'll see what the answer is. So this is of particular phenomenological interest because of this, as I said, it's a Sitter vacuole KKLT, and because of this warping, the supersymmetry breaking at an exponentially low scale, and this also it has been used as models of inflation. So this is a model that has been highly used in the literature. So what is the strategy? So unfortunately, this problem of localized branes here, it's by the techniques we have today, it's impossible to solve. Maybe in the future, one will hope to solve, or at least not to solve, but maybe get some answers for the localized solution. But what we are going to do is to smear these anti-D3 branes on the S3. So there's a smear density there's a smear charge, or a density whose total charge is the number of anti-D3 branes. So then the solution depends on a single variable, which is the radial variable away from the tip. Then we're going to impose D3 bar IR boundary conditions and then see what happens. So the solution again depends on a single variable, which is a radial variable, which we are actually going to use tau, which is the variable that Klebanov-Strassler used, and it's related in the UV to R in this way. So, and the solution preserves all the symmetries, like this, placing this doesn't break the original symmetries of the Klebanov-Strassler solution, so it preserves all the symmetries of Klebanov-Strassler. So there is an ansatz work proposed by Papadopoulos and Seiling, which is a consistent truncation of type 2b. The details are not important, but so the metric has a certain form. There's a topological 3-form flux on the sphere, and then extra modes and the 5-form charge. So this is, sorry, the 5-form flux. This is what's in the 5-form flux. This is the charge of D3 branes that goes in Ks to Q, to a constant Q, which is a number of D3 branes here when tau is much smaller than 1. And then in the UV it goes linear in tau, which in terms of R, this is the log R behavior of Klebanov-Strassler. So there are 8 modes in this parametrization. There are 4 that come from the metric, 3 that come from the fluxes, and then the dilaton. And we want to solve for a supersymmetry breaking solution. So a priori we have to solve the 8 second order equations. Now, so up to last night, well actually this work didn't start last night obviously, but up to 2011 we were working in linear order in n bar over m. So n bar is the number of anti-D3 branes, m are the units of 3-form flux, Ramon 3-form flux on the sphere, on the S3. And this is particularly simple because then one is doing a perturbation at first order around the solution that is supersymmetric. So we are perturbing the Klebanov-Strassler solution by a first order perturbation. And there's a nice tool worked out by Borokov and Gouser, in which the 8 second order equations split into 2 sets of 8 first order equations, because we're perturbing around this supersymmetric solution. So 8 of the equations are like this for some conjugate variable psi A, whose definition is actually the deviation. So this equation here, so this m is related to derivative of the superpotential. So here there is a superpotential that encodes a potential of this one-dimensional action. Once one reduces, or one can reduce all this as a one-dimensional system depending on tau, and there is a superpotential governing that system. And this psi measure the deviation from this equation is the attractor flow equation. So these psi variables, which are sort of the conjugate momentum to phi, they measure the deviation from the attractor flow equations. And then we have the equations for psi. And then the nice thing of this perturbation around the supersymmetric solution is that these equations decouple. So one solves first these equations, that they don't depend on psi because this is evaluated at the minimum, and then one solves these equations. These equations have integration constant that we call xa, And if xa are non-zero, the solution is non-supersymmetric because it doesn't satisfy the gradient flow, the attractor flow equations. And this integration constant we call y. So in the solution there is one distinctive mode which is related to the force on a probe D3 brane. So if we compute the force on a probe D3 brane, which is given by the difference between the Dirac-Born-Infeld and the Wess-Zumino potential and then the derivative of that, this is proportional to psi1, one of the modes. So out of the 16 integration constants, there is only one that enters here. So this is very nice because it depends only on one integration constant. And then also we have this full functional form. It's universal, so anything that exerts a force on D3 branes is going to have this form. And the UV agrees with the KKLMMT. We computed the force on a probe D3 bar from back reactive D3. So this is a very nice feature, and it will this piece will survive also for when we talk about the full back reaction, not at linear order. Now, so we solve at first order, and we have all these, the integration constants appear in the IR and in the UV with different powers. So here we divide it into normalizable and non-normalizable modes for all different operators, and we have a nice splitting, the constants x on one side, y on the other. So some give rise to normalizable modes, to non-normalizable modes. Some give rise to singularities in the IR and non-singularities and terms which are non-singular in the IR. So a couple of things. One thing here, I wrote this xa hat. This means that it's not exactly this x8 here, but it's just a combination of x8 and x1. So if we are going to kill this term because it's singular in the IR, doesn't mean that this term is 0, but it means that it's proportional to x1. And then another thing is that the y's here are in blue and here they are in red. This is because they come, so these are from the IR expansion, these are from the UV expansion, but we have the numeric coefficient that relates the IR to the UV. So we have all the solution at linear order from IR all the way from IR to UV. So there are 16 integration constants, as I said, but actually 2 of them are non-physical, or one goes away by the zero energy condition, and then one is a rescaling of 4-dimensional coordinates I will briefly mention afterwards. So there are 14 integration constants. So now let's impose D3 bar IR boundary conditions. And again, this Y1 is these two are the gauge degrees of freedom. So one from the zero energy condition, and the other is a rescaling of the 4-dimensional coordinates. And then all these other are singular in the IR, so we're going to kill them. And if you look at the UV, they give rise to normalizable modes in the UV. So actually they are fine from the UV point of view, but they are not fine from the IR point of view. So this we're going to kill. Then you can see other singularities in the IR, but this Y7 is fine because it's a singularity in F5. And this we expect because we have D3 branes, they couple directly to F5. So this we expect. Actually we do impose that this is non-zero. And then the other term that appears singular is the term that is we call the force mode. So this x1, if we set this x1 equal to 0, then there is no force on D3 branes. So this cannot correspond to the solution for anti-D3 branes. So this x1 has to be there as well. And we demand, so these are the things that we demand. These are our IR boundary conditions. So we demand that the Ward factor has a singularity. So it goes like 1 over tau, which is how it should go for D3 branes mirrored on the S3. And then we demand that the 5-form flux has this constant, minus n bar, so all the way at tau equals 0. So these are the only two things that we demand. And then this fixes Y7, this Y7, the charge mode. So in the UV, it goes like a log. This is a charge mode. This fixes Y7 to be basically minus n bar over m. And this also fixes x1 to be n bar over m. Now, this is fine. I mean, this x1, we say it appears as singularity. So this appears as singularity 1 over tau squared. It's fine because it's actually this singularity here. X1 appears here, so that's fine. But also x1 appears as a 1 over tau singularity in the 3-form fluxes. In the mode of, so F3 squared and H3 squared, they go like 1 over tau squared. So this is a singularity, a crucial singularity that we will talk about later. The question is it an acceptable singularity? We believe it's not, but for the moment let's pretend it is and let's keep going. I'll tell you more about the solution and then we'll go back to this singularity. So now if we look at, so this, again, this singularity, I haven't talked about the UV so far at all, so this singularity is there already. From imposing these 3 bar IR boundary conditions, we get this singularity. So now if we also look at the UV, there are all these modes which are regular in the IR, but they give rise, they are non-normalizable in the UV. So if we want to kill all non-normalizable modes except this charged mode, then we get that all the integration we have all the integration constants in terms of n bar over m. So we have the full solution. I don't want to get into let me say one thing. So the modes that are turned on in the UV are this operator trace of f to the 4th, which is directly related to anti-branes. This was identified before. Then there is this operator trace of vacuum expectation. Sorry, not operator. The vacuum expectation value of trace of f squared. Then there are also Gaussian bilinears that are turned on. Then there is a charge mode, and then there is this gauge degree of freedom. So this is a UV of the linear solution. It has all these modes turned on. So, well, there's sort of nothing wrong. So this is unexpected, but then apart from that, there is in principle nothing wrong with this. Let me say one more thing before we go to the full back reactive solution. There is some interesting feature here, which is the charge. So if we look at the D3 charge at first order, and we put 1 anti-D3 brane, this is -1 in the IR, and then it goes to some numeric value, which is -5.641A, blah, 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 it goes on. So this is interesting, because actually, this is unexpected in a sense. What it means is that the throat has to be is actually longer than what one would have thought. And so let me tell you how it goes. For example, if you compare the mesonic branch to the baryonic branch, so these are 2 branches of the same solution. So this has m D3 branes, and this has no D3 branes. These 2 solutions have the same charge in the UV because this has m D3 branes, but this has a longer throat. So whatever the charge that is here on the branes, it's the same charge that is here dissolving fluxes. So one expects these 2 to have different to finish. So the radius of the S3 is smaller for this than for this, and this was also found in the gauge theory. So this is fine. And what we are finding here is since this in the UV has an extra negative charge, this extra negative charge has to be compensated by a longer throat. So the throat is longer, and it's longer by this number that's not, it's not an integer, it's not anything. So that's something curious. Another curious thing is that the throat can be made exactly as one expects, but then instead of so this Y1 that I say is a gauge degree of freedom is actually related to the size of the S3. So in this solution, this Y1 has a particular value proportional to n bar over m. But instead of doing this, one can turn on Gaussian masses, so turn on these non-normalizable modes, and in some particular combination, which again is given by some number, non-rational or anything, and by doing that, then one gets the charge in the UV to be exactly the same as in the IR. So that's curious, and apparently that's interesting from the point of view of making this model compact. So in that case, the throat is the same throat, is like here, it's the same throat as a baryonic branch. And you don't have to, the throat doesn't get longer, and the charge also goes again to -1 in the UV. Okay, so now let's go to the IR singularity. So this IR singularity is present in all the systems that we studied, which are many by now. So we studied anti-M2 branes in the Ward tensile space, where there's a proposal, the analog of Klebanov-Strassler was proposed by Svetish, Gibbons, Liu, and Pope. And then there is a KPB proposal, so Katru, Pearson, Berlinder type proposal by Klebanov and Pufu. And this system has the same singularity. It's even worse than the one we had. Also in anti-D2 branes in G2 holonomy manifolds, this again has a worse singularity than we have. And also in anti-D6 branes in T3 times R3s. This can be thought of as toy model for the dual of this. So if we dualize the anti-D3 brane on the S3, then we will get an anti-D6 brane on S3, but a simpler model is this, and this model has been studied by these people in lots of detail. So there are many things that one can study in this model that cannot be studied, or they are much harder to study in the anti-D3 brane model. So this model was used for inspiration in many ways. So some people were trying to convince us that this is an artifact of perturbation theory, and indeed that some of the singularities seem to arise just from perturbation theory. But all of the singularities, is that true that this is an artifact of perturbation theory? And now we have the answer, and the answer is no. These singularities are still there in the full solution, and it's actually not so hard to show. So in the full back reactive solution, so we don't have the full back reactive solution. We have the solution. We have the solution in the IR, but actually you don't even need the full solution in the IR to see these singularities. But the idea is that the full back reactive solution will be something like this. So we impose anti-D3 bar conditions in the IR, and then in the UV we hope this should be Klebanov-Strassler plus some normalizable model. So this is sort of red in the IR and blue in the UV. So this charge has to go from anti-D3 from negative to positive. This, the full back reactive solution uses the same ansatz because it has the same, the same symmetry. So we use these 8 modes, and again we're solving for we're looking for a supersymmetry breaking solution. So there are 8 second-order equations that we have to solve for these modes. But again, we're going to use sort of the trick of Borokov-Gubser, which is here just a useful trick of separating this into 8 first-order equations. Now the difference is that these 8 first-order equations are not these 2 sets of 8 first-order equations, now they are not decoupled. So you can see here, for example, this is now how it looks, the equation for the xi. So first it's nonlinear, this term wasn't there anymore. And then before here, this was linear because the supersymmetric solution, the Klebanov-Strassler, has xi equals to 0. So this was linear, so this was evaluated in the background in the linear solution. So there weren't any phi's here, and that's why the system was decoupled. Now it's not decoupled anymore because we're not solving a linear order. So this equation for xi contains the phi's. This equation for, well, this equation for phi obviously contains the xi's. But it's still useful to do this, and the xi's are defined as before. So they are the deviation from the gradient flow equations. So in xi non-zero means the solution is non-supersymmetric. So again, there is one distinctive mode, which is a force on a pro D3 brane, which is again computed as dBi minus U sumino. So at the linear order it was this, and this is the same at all orders, except that this x naught gets replaced to the full x. So this is one of the metric modes, and this is xi1, the same as before, one of the xi's. So this is exact, and this is nice. So there is one, the force is proportional to the integration constant of this xi1. And actually, there's something that is very useful, which is to compute the force on anti-D3 branes, which is a dBi plus a U sumino, and this is given by this, but instead of xi1, it's something that we call xi1 bar, which is, it's not, bar should not be confused with a complex conjugate. This is defined as xi1, but in the superpotential of this system, we just have to change a few signs, the sign of F5 and the sign in H. So in terms of the functions that appear in the superpotential, it's just changing a few signs. And this means in terms of solution to this, if Klebanov-Strassler is a supersymmetric solution of this system, then anti-Klebanov-Strassler will be a supersymmetric solution of this system. So, and these are useful variables to work with. So one can work with this or with this. They are both useful depending on what one wants to do. And now we're going to impose D3 bar IR boundary conditions. So the conditions that we impose are exactly the same as before. We impose that the war factor has this 1 over tau singularity, and the phi form flux very near the tip is this. So notice we're not imposing that the 3 form flux is imaginary anti-self-dual or imaginary self-dual or anything. We're just imposing this. And then now let's impose that there is no singularity in the 3 form fluxes. So it can be anything it wants, but just not singular, because this singularity is not directly sourced by the D3 brane. So if we impose this, then it's not hard to show that if you expand this psi1 bar in powers of tau, so in the IR, what you get is actually that all these psi1 bar are equal to 0 for all n. So this psi1 bar is equal to 0. So there is no force on probe D3 bar branes, and this means that the solution is anti-Klebanov-Strassler. So you demand that you demand this and no singularity in the 3 form fluxes, and you get that the solution is anti-Klebanov-Strassler. So what we thought, the solution that we expected to be this way, that really doesn't happen, and the solution by this boundary condition here and no singularity in the 3 form fluxes, you get anti-Klebanov-Strassler all the way. So let me say that this solution exists beyond perturbation theory. It's not that it's not there, but it has singular 3 form fluxes. So it's demanding this singularity, this absence of singularity in the 3 form fluxes that kills this solution. So this solution it's there, we have it in the IR, but it has singular 3 form fluxes. So to conclude, so anti-D3 bar branes in Klebanov-Strassler lead to a singular solution. By singularity, we mean again singularity that is not the one directly sourced by the D3 brane. So these are IR singularities in the 3 form fluxes. And the only non-singular solution with anti-D3 brane boundary condition is anti-Klebanov-Strassler. So to be or not to be, this is a question, and I think this is the answer. Thank you.
Okay, we have time for lots of questions.
Melda. Well, I know this has been debated for a couple of years, and so I guess this is, from an outsider, I guess this may not be the last word. I guess it is. So how do you expect the reactions to this?
I have an next transparency. So yeah, we didn't finish last night, but they still work. So the question is whether this singularity is physical or not. So in order to be physical, it has to be resolved in string theory in some way. So the only way to resolve this singularity is by brane polarization, I think. So this singularity could be resolved by brane polarization. And this is the next thing that we're going to study. But we have, so let me tell you. So we have, so it's a sort of belief, and the first results seem that this is the case, but this is too preliminary to say that the branes don't polarize. So the question is, can brane polarization cure it? And maybe, but maybe not. And we think not. So these are the 2 polarization channels. So there are always 2 polarization channels, and the 2 polarization channels in this case is one is the NS5 brane that I talked about, but this is wiped out in the smear solution, right? Because we're smearing this on the S3. So you have a brane wrapping this S2, another wrapping this S2, another wrapping S2. So this is not, we don't see it in the smear solution. But this was when we first talked about the singularity. People say, oh, that's a singularity because actually what's happening is a singularity in the NS3 form flux. It's a remnant of the NS5 brane that is there. So that makes sense, except that the singularities are in all possible legs. So they don't correspond to the legs of this, but they are in all possible legs, and also in the Ramon 3 form fluxes. So we thought, and we still think that brane polarization most likely won't solve this. But so the thing that we're studying now, we're trying to study, is this other channel which is visible in the smear solution, which is the D5. So here there is an NS5 brane wrapping NS2 inside the S3, and here there is a D5 brane wrapping DS2 and at finite radius. So this polarization channel is seen in the smear solution. The problem is that this is non-perturbative, so it needs a full back reactive solution. Unlike this, that can be studied even in the probe approximation as KPBV. For this, you need a full back reaction. And we have it in the IR, and you need a little bit of information on the UV. And here is when, again, this work, this toy model comes very handy, because in this toy model, Joseph, Jungans, Kupperstein, Van Rietvase, and Sagerman studied this year what happened in the anti-D6 brane in T3 times R3. And here there is no polarization. So it could happen because all the ingredients are there, but it's just there's a square root, there's a quadratic thing that you have to minimize, and there is no minimum for that. So here it doesn't happen. And since this turned out to be a very useful toy model, and we believe it captures the IR very well, it's simpler and it captures the IR very well. So we have reasons to believe that it won't happen here, but this is, this is the next thing that we're going to study. And I guess, I don't know, maybe if after this people keep saying that the singularity is physical, then I don't, then we will.
Yeah, you discussed everything with smeared D-branes, but usually D-branes actually localize. So what are the chances of doing it with the extra broken?
So first, we don't think that the problem is mirroring, but it would be nice to show it. And again, this toy model is nice because here the branes are localized and all the singularities happen there. So one thing, so we were actually hunting for, so the way we showed that the solution is anti-KS is by what I showed, like psi 1 bar, you can show that it's 0 to all orders. But there also in this D6 bar model, there is also some what they call some topological argument to show that so you have certain boundary conditions in the IR, in the UV you want the solution to be well Klebanov-Strassler would be, and you can show that if you demand absence of singularity, then these two regions cannot meet each other. And we're hunting for a topological argument of that type, which might be used in the localized solution. So that's, I think, the best hope of saying some, at least so far, saying something about the topological solution. We sort of found arguments, but they were actually more complicated than solving themselves. So far, we said, we don't have a very short, nice topological argument that one can use in the localized solution, but hopefully that will come. Then I don't think really solving the fully localized solution is realistic.
So okay, so I'm also an outsider on. Okay, so there's all these kind of long, detailed calculations of these enormous equations, which I can't follow. So is there kind of like a shorter kind of like, is there kind of like a physical reason why the anti-D3 isn't physical?
Logs. Joseph will tell you log. That this gives a log contribution. This is like a two-dimensional system at the end of the day, and you're just doing some. There are two types of things one could think. So one is that, or actually there are two types of end results of this. So the system is not metastable, so what happens? So it's not stable, so what happens? That's it. The two possibilities. One is that the solution is anti-KS. So you just put, I don't know, 3 anti-D3 branes, and then the solution is anti-KS. It just changes, flips the sign of all the. So that's one possibility, and then you could sort of understand, because this is like a two-dimensional system, and you're pinching a little bit the drum, and then it propagates all the way. So that's one possibility. And then the other possibility is what the anti-D6 people have been claiming, that which is that the singularities are because the brane attracts imaginary self-dual flux, and then you saturate the bound of. So in the KPB, so the KPB, the probe approximation of KPB. So in this calculation, it works for P, or sorry, I call it M bar over M less than 80%. And they say, so what happens is that this attracts imaginary self-dual flux, and it's such that it saturates this bound, and then this decay happens perturbatively. So what happens is that they annihilate towards the flux. So either another possibility is that it forms a black hole, but Yossi Ben and Oscar Diaz, they are showing that doesn't exist. The black hole with negative charge, with the opposite charge of the background, is not stable either. So these are all the possibilities, and it's just I mean, there's an awful lot of charge with some sign, and it doesn't want to be there on that sign. I mean, to be honest, I believe more that that this happens perturbative and it annihilates towards with the flux.
Also private passes off
Okay, so this is the next.
What was the question?
If alpha prime FX could solve the singularity, I haven't thought about that, and I don't know. That's a good question.
Well, let's thank the speaker again.